In this video, we're going to analyze the effect of unmatched loads on reflections off the input of a two-port network. This is an important lens for analyzing stability because reflections off of each port are crucial factors in determining stability. I've drawn a two-port network here that has a mismatched load. That means we need to define a reflection coefficient off of the load, and we've done so in the form of gamma L over here. The source is matched in this example, so gamma S is equal to 0. We're curious what a reflection off of the in port looks like now that we have some additional power coming into port 2 from load reflections. As a reminder, gamma in was just equal to S11 when the load was terminated. But now we have some additional behavior. We're going to call the effective reflection coefficient gamma in. We can start by writing one of the equations that define S parameters and observing that we need to find B1 over A1. However, to find B1 over A1, we'll need to eliminate A2 from this equation. So we write the other equation that defines S parameters to do that. And we combine that definition with the fact that waves leaving port 2 get reflected off the load, creating a round trip. We can substitute that into our equation, then rearrange it to find B2, then finally find A2 by remembering that it's created by B2 reflecting off the load, so we multiply our prior expression by gamma L. That gets substituted into our first equation, which leaves us tantalizingly close to finding gamma in. Factoring out A1 and dividing both sides by it, we find that gamma 1 in is given by S11 plus some additional amount that depends on the product of S12, S21, and gamma L. I find that product somewhat intuitive because it's the set of reflection coefficients A1 sees as it takes a round trip coming back to B2 through the S parameter network, the reflection coefficient, and the S parameter network again. Finally, note that we could find the reflection behavior of the opposite port by swapping S11 and S22 in this equation. This is the most important equation to take away from this video. However, there's an alternate way to write gamma in that we do need to derive now. We can combine S11 with the second term by multiplying and dividing by the denominator of the second term. Then we can factor out gamma L and gather like terms, which results in this kind of interesting difference of products. That difference of products is the determinant of S, and we often give it the symbol delta. So we can write gamma in this alternate form that depends on the S matrix determinant. In summary, the reflection off a port in an S parameter network depends on how much mismatch there is in the load. And I've written the two expressions for that here, including alternate forms that depend on the determinant of S, which we labeled delta. And we see this dependency because of signals taking a round trip and bouncing off the load, then coming back to the input port, which is a kind of feedback, so you might imagine that this input reflection coefficient behavior is important for stability.